Okay, so this is primarily graphical antiderivatives, but there's also tables and things like that. So we're going to work through problems that are similar to the ones on your worksheet. But before we do this, I want to remind you of how to do the derivatives graphically. So if we have f and we want to find f prime, let's remember what happened. Okay, so let's start with a function that's made out of just line segments. And line segments is actually two kinds of functions, because the horizontal ones are actually constants, and then the tilted ones are actually like the line segments you would think of. It would be nice if my computer would listen to me once in a while. Okay. I think I have my pen back now. Okay, so this is f in black, and I'm going to use blue to make f prime. So first, the derivative from here to here is 0. F is 1, but the derivative is 0. And likewise, from here to here, the derivative is 0. So that much we know. We know that the derivative changes when we transition from one line segment to another, but since they're all line segments, within each region it's going to be a constant bit. Okay, so we have a slope of 1 in this region here, and then we have let's see, a slope, it's going 1, 2, 3, 4, 5, 6 by 3. What's that? Okay, so rise is -6, run is 3, so that gives us a -2. So the slope of this guy is -2 over here. And then what do we have for our last line segment? We have the rise is what? 1, 2, 3, 4, 5, 6 over the run of 2. So the slope is 3 over here in this segment. So this is what we end up with. So if we started off with line segments, what we're going to end up with in our derivative is also line segments, but they're all horizontal line segments. Okay? Hopefully that's good for you. And let's move on to another example where they're not made out of line segments. Okay, I just tried to make a fairly symmetric curve, and one that I think the derivative in the middle should look like it's 0. This function is first increasing, so your derivative is going to be somewhere over here, and then the function is decreasing, so it's going to be somewhere down here. Okay, well that much I know. And if I'm looking in this range, the function should have a +1 slope, so I'm going to put it here. And in this region, it's going to be -1, so I'm going to estimate it down here. And let's see what else. Right around here, I'm going to estimate -1/2. And right around here, I'm going to estimate -1/3. And I'm going to do the same thing on the other side because it's symmetric. This, I'm going to estimate it's about 1/2. And around here, I'm going to estimate it's about 1/3 down here. So what I'm going to do is kind of connect the dots. And I've done this before, but it takes a little bit of practice. But you just kind of smooth that out. If your original curve looks like the variation is happening smoothly, you just make the variation on the derivative about as logical as you can. You put some points in there to sanity check what you're doing. Make sure that if any time your original function has a max, that you're cutting through the 0 on your f prime. Double check that any time your function is increasing, your derivative or your claimed derivative is positive, and vice versa. When your function is decreasing, make sure that you're below the axis. And then just kind of guess what it's doing. So we don't expect you to have these things perfect the first time, but you kind of work with it and it grows on you. Okay, so now we want to reverse this process. That's just a review. Now, let's reverse this process, but it's very much the same kind of thinking. You have to say, well, what was I thinking when I was doing that forwards derivative process? So I'm going to just do the opposite if I'm going to take an antiderivative. And by the way, when it says take 2 antiderivative, it doesn't mean take the second antiderivative, it just means take the antiderivative and nail it down somewhere, and then your second antiderivative will look the same. It'll just have a different starting point. So that's what that means. Okay, so just like in our first example before, what we ended up with when we took derivatives was a whole bunch of horizontal line segments. So let's start with a whole bunch of horizontal line segments and see if we can take the antiderivative of that graphically. So let's see, let's try some line segments, and I'm just randomly making this up to see what happens. This is kind of hard to see, so I'm going to go over it again. Let's try that. And now you need a starting point. That's like saying you need a starting point to say which mile marker did you start at. But the shape doesn't matter. That's the whole point. The shape isn't going to matter. Once you have your starting point, all the antiderivatives will look the same. So I'm just going to start right here just for the sake of argument. So the blue one is f prime, and we want now the red one to be f. Okay, so for 2 units we have a slope of 1. Okay, let's do that. Now for 2 more units we have a slope of 3, and I'm going to slide all this stuff down if you don't mind, because I just think I need more space right now. I'm going to be growing a lot. Thank you. Okay, so I need a slope of 3 now for this next part, so I'm going to go up a total of 6. I'm going to go up 3, and I'm going to go up 3 more. Okay, next I'm going to have a slope of 2 for 1 unit. And then I'm going to have a slope of -1 for 3 units. Thank goodness. Then I'm going to have a slope of 0 for 2 units. Then I'm going to have a slope again for 3 units, a slope of 2. Oh no. How am I ever going to do that? I'm going to push this down further again. Hopefully I can make it. So 3 units, and I have to go up a total of 6. Okay, then I'm going to increase with a slope of 1 for 2 more units. So that's what I get for not really planning this out in advance, but hey, that's what that looks like. Okay, so think about that and make up your own function and see what it does. Okay, I'm afraid that I made another one of these functions that's sort of top heavy, so I'll just have to squish it down here and hope I didn't make it. Well, I guess I'll just keep moving it if I have to. Okay, I'm going to start a little lower in this time just so I have more room to draw this picture. So first I have a function that has a slope of somewhere between 2 and 3, maybe 2.5, but it's an increasing slope. So it's going to be looking that kind of shape. It's going to have an increasing slope that varies between being 2 and 3. And so it's going to wind me up somewhere between here and here. So I'm going to try to make it steeper at the top and less steep at the bottom. And it's kind of hard to really make that variation very visible. I'm going to do the same thing in reverse. I went too far actually. I wanted to go kind of halfway between. So I wanted to be less steep and then more steep. And then I want to reverse that and again go about 2.5 units. So I'm going to go, let's see, to about here. No, maybe about here. And so I want it to be more steep and then less steep. Okay? And that's what I'm getting from that little semicircle. It's kind of like an S shape like that. Then I'm going to have initially a positive, this guy is the f, and this guy, f prime, and this guy's the f. Okay, so this slope from here to here is varying, and it has an average of 1, and it's increasing. So I'm thinking it starts at 2 and goes to 0. By the time it gets to the top, it's going to be flat. I'm going to start turning around. So if the average of that guy is about 1, I'm expecting a slope roughly like this if it were totally 1. And on a picture like this, there's not much I can do. I know I'm going to end at 0, and the average is going to be 1, so I'm just going to kind of draw it like that. And now we have the same little S shape that we had on this curve, we're going to have on this curve, but just kind of in reverse. And so I'm going to go ahead and do that. And before, I decided to make a net increase of like 5 units when I did that. So I'm going to go down 5 units. And it's just kind of an estimate. So I'm going to try to end up down here. This is roughly in the middle, so I'm going to kind of sketch this thing being steepest right here. And that's reasonable for what I'm trying to do. It's not perfect. Now let's see. Now I'm going to increase again. And I'm going to look at the area under this triangle. And that area is 3. So I'm going to increase a total of 3 over the course of this traverse. So 1, 2, 3. I should end up here actually, but it should start off gentle and get steeper, so it'll look kind of like that. And then the slope is going to stay the same. I don't want it to be too steep over here, maybe like that, because I have to maintain whatever that steepness is for 2 more units. So like that, maybe like that. It has to look natural, like it's continuing from whatever I did over here. Okay, now make it straight for 2 more units. Let me see. Something like that. Okay, now what do I do? Now I'm going to decrease the slope, but it's still positive. And when I get down here, my f function should hit a max. So what is it? It's approximately an average of 1, is approximately what the slope average is. And so on average, I'm thinking I'm going to go like this and hit a max. So I'm just going to round this out a little bit to make it look prettier. All right, so now I hit my max, and now I'm going to go down. And again, it's kind of an average of 1. So it's going to kind of look like that. But I want to round it out so that it gets steeper as I get to my destination. So it's going to be steeper than 1 when I get to my destination and less steep at the beginning. So it's going to be rounded out like that. So your homework will look not too terribly different from that. So have fun with that, and don't expect it to be perfect. But the point is, you do it and then you try to do it backward. You say, well, now that I have f, if I take the derivative, do I get back to the original function? Okay, you have a question on your homework that looks similar to this, and there's a starting point that's also given. So let's just, for the sake of argument, start at 100, just like in your worksheet. Okay. Now what we're doing is we're essentially, for this, I'm asking you to use trapezoids. Okay, so that's the best you can do in the given situation. We don't know anything about the derivatives of this, and it just seems like we don't know enough about this function to even take other points into considerations. Given the tools we have, it's not too bad to use trapezoids. So what you're thinking is, you're thinking of, here's f, and at 0, f is 100. So you have a point 0, 100. All right, and it looks like it's increasing 1, 2, 3. And here at the beginning, your derivative is 5, but by the time you get here, your derivative is 7. So, but we don't really know where the trapezoid goes, so it's a bad way of saying it. But I want you to think trapezoid. So if you were going to kind of average between 5 and 7, you're going to guess that in this range, we're going to guess that f prime is approximately equal to 6. Right, so we're going to use that estimate, and then draw a trapezoid. So slope is equal to 6 here, but you're going 3 units, so you're going to get up to 3 times 6 is 18, so 118. So we're going to assume that we arrive at 118, and then there's essentially some kind of trapezoid that that we're filling in. Okay, does that make sense? Hopefully. Okay, now notice these x values are not equally spaced, but the f primes are, and that's just to make the calculation easier. So I'm going to guess f prime is equal to 8 here, and I'm going 3 units, so 3 times 8 is 24, so I'm going to assume I'm going to go about 24 units. So that's going to be about 142. All right, then I'm going to go to the next one. I'm going to say, okay, guess between here and here, f prime is approximately 10. We're going 2 units, so it's 20. Add 20 to f. And then from here to here, f prime is approximately 12. Now, you're not going to necessarily have things that are spaced by 2, so take the average of whatever those two values are. That's how I'm finding the estimate. All right, and my distance is 4, so I should add 48. If my slope is about 12. So that should be about 210. And unless I did the calculations wrong, that's what I'm saying. I'm estimating this. Okay, so that's my guess as to what f should be, and that's the process that I'm expecting you to use on your worksheet. And one of the things, you have actually several questions on the back of the worksheet, so make sure you do both sides of the worksheet. I know we've been getting kind of spoiled with short worksheets, but we're having some long ones at the end. Okay, so if your function, let's say g or f or whatever you call it, I'm just going to call it f prime, and we're looking for f, you need some kind of starting point, but you can put it anywhere you want. If you look at this guy, it has a derivative of 0. So f prime has a derivative at 0. So that means f has a point of inflection here and here. So when you're looking at your original function, f, think about this. Where the derivative has a derivative that's equal to 0. The second derivative is equal to 0. So your second derivative of f is going to be 0 here, so f is going to have a point of inflection. But what about these special places? These special places mean that f either has a max or a min. Well, in this case it's a max, in this case it's a min, and that means over here you're probably coming out of a min also. You can kind of imagine that you're coming out of a min here, and you're coming out of a max here, but you just stop there. So that's just something to keep in mind. You're going to stop short. You're not going to do a turnaround. So how do you know which one is which? Well, if f prime is positive up here, so f prime is positive here, and f prime is negative over here, and then flat. So if f prime is positive, and then flat and negative, that means you have a max. If f prime is negative, flat, and positive, then you have a min. So again, over here, f prime is negative, and here, f prime is positive. And so that's how you end up with a min. So hopefully those clues are enough to get you on the right track for that question. And this concept, I want you to know the wording, a specific type of wording, a classic calculus word problem. Students get used to derivatives and they imagine area, which is great. But when you really want area, it's a little trickier. Sometimes. Okay, So for example, if what you have is a function that's strictly positive, no problem. But the problem that you're being asked in your worksheet is something like this. There's some kind of function, and you can just go ahead and plot it. Whatever it is, plot your function, and it's going to ask you for the area between the curve and the axis. So between the curve and the axis means these areas. So if you have a between the curve and the axis problem, so we have a between the curve and the axis problem, and those are classic problems, but you have to first take f of x and break up the interval based on where the zeros of f are. So in this case, you're going to integrate, let's say this is a, b, c, d. I'm going to use e for lack of a better letter. So you're going to integrate f of x from a to b. And that's going to give you this first area. But then the problem is this area is negative, so then you're going to say minus the integral from b to c, f of x dx. Or you could do something else like put b on the top and put c on the bottom. That's fine. But you have to do something, and you have to just be aware that it's happening. C to d is going to look like the first integral, and you just have to keep doing this as many times as you need to. Okay, so you have to be aware of when that flips so that you can change the sign, and then you add all those pieces together, and then you have the area between the curve and the axis. So it's a little trickier than just taking the integral, but it's in every calculus class, and so you should be aware of that problem prototype. All right, and that's it. That's it for this worksheet. Go have fun working on the worksheet, and I'll see you in class.